But what's the point? Well, look at the difference between these two curves. Okay? What's the difference between these two curves? Well, this one, the curvy part, kind of points toward the origin. This is 0, the origin. And in this case, it kind of opens up. Okay? So if I draw my secant over here, that secant is above the curve. And if I draw my secant over here, that secant is below the curve. If my secant is above the curve, if it's above the curve, we say that this line is convex to the origin, to 0, to the origin. And if it's below, we say it's concave to the origin. Now, if you want to bear that in mind, I had a math professor who used to say, think of this as a cave. You're going into it, right? It's a cave. So that reminds you that concave is facing toward that and convex is facing away. I don't know if that helps you. That always helped me, the cave idea, the visualization of the cave idea. So we deal with lots of curves in economics. Some of them are convex and some of them are concave, and it's important for us to understand the implications of that. For example, what we're going to call a isoquant, or we draw a lot of lines where we have, equal utility along that, or equal output along that, equal production. That curve has different outcomes than that curve has, to know whether it's convex or concave. Okay, are we excited by that? So an indifference curve looks like this. And indifference curves are curves which you may have hit them already, hopefully. You took 302. But an indifference curve is a curve where the utility on it is always equal. If this is your utility curve, you're really messed up. If this is your indifference curve, then maybe you're okay. And we'll get to why that is, but you have to sometimes know the difference between concave and convex and what that means. Okay? And there's all kinds of other concaves and convexes you'll get to in life about quasi this and, but it's very exciting. This also shows up in things like demand curves. So we actually have a curve called a rectangular hyperbola. Which is, obviously, we could do this, but we're not, convex to the origin. Rectangular hyperbolas show up in two very specific but interesting cases in economics. A rectangular hyperbola is when x times y equals a. So I just take x, right? This is x, and this is y, and it's a constant. So price times quantity is some constant number, for example. Do we like that? So if the price falls in half, the quantity doubles. Okay? So the two ways this shows up in our world is what we call unit elasticity, which means the price elasticity of demand equals 1. Then we get this rectangular hyperbola. The other rectangular hyperbola we see is the average fixed cost curve. Is that exciting? Because fixed cost, yes? So if we draw a line of average fixed cost, it's going to look like this rectangular hyperbola thing. Is that exciting? Okay, you're like, what's the point of this? And mostly the point of this is to take you through some math that hopefully you've seen before and get you all happy doing math again. No? Okay. I know, you're so excited. Okay. We can also, we'd already done functions, and let's just write a function out. So we said y equals a function of x. So if we say, y equals 10 plus 2x, that's that. Y is a function of x, or y equals x squared. That could be that. Any function that we come up with that's got y over here and x over here. Okay? Very often, though, we're going to deal with something that looks more like this, where we have z as a function of both x and y. So we might have, z equals 10 plus 2x minus 3y, and that's our equation. And we could do that for 3 variables or 4 variables or 5 variables or however many variables we want to have. Most of the time in this class, we're going to deal with functions that have more than one variable. And the reason why we're doing that is they're very difficult to graph. So this is easy to graph, right? Is that, and that is, and those are, I can graph those. But to graph, so I can put 2 variables, right, x and y, I can put those on a flat surface. But 3 variables, now I need an x and a y and a z line, and I have a line that's actually coming. There's a line, you can't see it, but there's a line that's coming straight out at you from that point. Okay? And so we draw that so it looks kind of like this, and this is, x, and this is y, and this is z, and then out here in space somewhere there's a point, right? Don't even ask me to really do those things, okay? And if we have 3 variables, or 4 variables rather, x and y and z, then we need a 3-dimensional space to draw it on. So we can only effectively graph things with 2 variables, with an x and a y, and we can sort of graph things with 3 variables, with an x and a y and a z. We're hopeless beyond that. Okay? We live in a 3-dimensional space. A 4-dimensional object could have a shadow that's 3-dimensional. Theoretically, physically stuff, but okay? So we can't do this in graphs, and that means we have to do it how? We have to use math. Yay, go math. So we can do all kinds of fun and interesting things, right? Let's suppose we're given these 2 equations, and somebody says, find x1 and x2. Okay? Can we do that? Well, of course we can. Okay, because we're mathy whizzes. So what we need to do, there's a bunch of different ways we can do this. Okay? We're going to come up with cooler ways to do it than you learned in elementary school, right? When you did this, or whenever you learned how to do them. But we can say what? We can multiply this second equation times 2. All right? And so we have 5x minus x1 minus 3x2 equals 28. And we have, that's a times, not a x. We have minus 4x1 plus 8x2 equals 28. Ooh. All right? So we could do that, and then we can play with it. No? You don't want to do that? The easiest way to do this is say, all right, take this. Let's go over to the next page. And 2x1 plus 4x2 equals 14. Let's take this equation and solve it for x1. Can we do that? So I've got minus 2x1. I'm going to take 4x2 and subtract that out of both sides and get minus 2x1 equals 14 minus 4x2. Okay? And then I'm going to divide the whole thing by minus 2. So I get x1 equals minus 7 plus 2x2. Is that exciting? Okay, you're like, yeah, and you know what's coming, yes? We're going to take 5. We're going to multiply 5 times minus 7 plus 2x2. Why? That's an x1. So that's x1, and I can put that x1 right there into this equation. Yay! Yee! Okay, now I can solve this. So I've got minus 35, and I really wish we were doing this in class, and I bet you do too, plus 10x squared minus 3x squared, x2, minus 3x2 equals 28. So minus 35 plus 7x2 equals 28. Add 35 to both sides. 7x2 equals, 63. x2 equals 9. We get that? I divide by 7, and I divide by 7. Okay? Well, if x2 equals 9, what does x1 equal? So 5x1 minus 3, 9 equals 28. So 5x1 minus 27 equals 28. x1 equals 45. Right? I add 27 to both sides. Sorry. I don't know what I'm talking about. Add 25 to both sides. So 5x1 is 55. So x1 equals 11. Does that work? Hopefully you followed that mess. So again, I really wish we were in class. I tried going into the classroom and writing on the board and videoing it, but I wasn't a big fan of that. So what did we find out? What did we get? We got 9 for x2 and 11 for x1. So 5 times 11 minus 3 times 9 equals what? Well, that's 55 minus 27 is 28. Minus 2 times 11 plus 4 times 9 equals 36 minus 22 equals... Oh, we're so good. Okay? Yes? You're like, why are you doing this to me? Let's do it again like we did last summer. 7x1 plus 2x2 equals 60. And you're saying, why don't you write this down and give it to us? Because you're not going to learn it that way. You need to write this down, and you need to go step by step while I steppy through this with you while we figure it out. Okay? So this is even easier because x1 is all here by himself. So I'm going to take this equation, right? And I'm going to subtract 8x2 from both sides. So x1 equals 78. x1 equals 78 minus 8x2. All right? So now I take 7 times 78 minus 8x2 plus 2x2 equals 60. We good? So 7 times 78, I know you're like, why did you do that? Well, it's good for you. No, 7 times 80 is 560, yes? So 7 times 78 would be 546 minus 56x2 plus 2x2 equals 60. Yay. So 546 minus 54x2 equals 60. Do you see that maybe this will work? Yeah. So we subtract 546 from both sides, and we get minus 54x2, yes, is 486 minus. We can ignore the minus signs, right? We can turn those both into plus signs. And x squared equals 486 over 50, or x2. I keep saying x squared, but x2 equals 486 divided by 54. And can we do the math on that? Do we know how to do that math? Do we know? Do we know? You got it? Is 9, right? So x2 is 9. If x2 is 9, what's x1? Well, 7x1 plus 2 times 9 equals 60. 7x1 equals 42. x1 equals 6, right? We subtract 18 from both sides. So 9 and 6. And again, how do we test it? Well, 6 goes in there, 9 goes in there, right? That's 42 and 18 is 60. 6 goes in here, 9 goes in there. That's 72 plus 6 is 78. And Viola, it works. Yes? Okay.